Hello everyone, I am Nicole Harrison with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Emmanuel Levy and Jordan Dents here today to discuss advances in manufactured home energy efficient design. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device when you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinar help desk for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate which speaker you are addressing the question to. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here and may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today. Making significant strides in energy performance in the affordable housing space is the holy grail for the research community. The work presented in this webinar is a collaborative endeavor by the ARIES Building America team and two major affordable housing providers, Habitat for Humanity International and the factory building industry. This effort is exploring options for making major reductions in space conditioning energy use while holding the line on home affordability. Specifically, the project will develop a high-performance integrated design, effectively combining an ultra-efficient thermal envelope, a very low-capacity, highly efficient mechanical system, and an innovative distribution system, and affordable heat recovery ventilation, and set in motion steps to rapidly move this innovation to market. Before our speakers begin, I will provide a short interview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Visit our website at buildingamerica.gov to find more information about the program and the Building America Solutions Center, which provides expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. Building America is supported by 5 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. And now on to today's presentation. Our webinar today is Advances in Manufactured Home Energy Efficient Design. If you would like more detailed information about this effort, please feel free to contact our speakers. Our first speaker today is Emmanuel Levy. Emmanuel is president of the Levy Partnership, a consulting firm providing engineering, architectural, management, and marketing services in building-related areas. Through the Levy Partnership, he works with companies in the U.S. and abroad and is a pioneer in building research, development, and product marketing. The Levy Partnership has served the home building industry for 32 years, generally providing technical support and advice to companies involved in home building, sales and marketing, and providing services to public agencies interested in developing new technologies for housing and accelerating their adoption by industry. The firm specializes in a wide range of areas, including new product development, economic assessment, regulatory analysis and standards development, strategies for incentivizing efficiency, diagnostics and field evaluations, energy modeling analysis, and feasibility studies. Included among the firm's clientele are utilities, leading home builders and home manufacturers, state and federal government agencies, major product suppliers, and trade organizations. Also presenting today is Jordan Dents. Jordan has more than 20 years of experience as a researcher and consultant to the building industry. His work is focused on building energy efficiency, demand response, and factory-built housing. Jordan is a lead project manager of the ARIES Building America team. He holds an MS in Building Technology and a BS in Architecture, both from the Massachusetts Institute of Technology. He is also a certified passive house consultant and ResNet home energy rater. With that, I'd like to welcome Emmanuel and Jordan to start the presentation.
Thank you very much. We're already challenged technically. Here we go. Okay. Thank you very much for that introduction. I want to just mention quickly that we are representing a team of groups of organizations under what's known as the ARIES Collaborative. It's made up of organizations that are primarily in the affordable housing space. And of course, we're one of the teams under Building America just mentioned. And the Levy Partnership is the lead for the team. So we were responsible for bringing all the partners together and getting the collaboration off the ground. As was mentioned, I'll be giving a short discussion of introduction to the project. I'm going to turn it over to my colleague Jordan, who'll talk about some of the technical results. Our presentation should last about an hour. I think if the process for questions was mentioned is if you have questions, type them in, and at the end we'll try to get to as many as possible. The presentation really traces the evolution of a project that started a number of years ago, and it was a project that was intended to fundamentally alter the manufactured housing industry's approach to energy efficiency. Interestingly enough, when we started the project, the industry, and this is the part of the home building industry that's often referred to as HUD code, manufactured homes or factory-built homes. This part of the industry was built to its own building code, and when we started the project, it was probably the worst off in terms of energy efficiency, and our goal through this project was to bring in a set of technologies that the industry could embrace and could do so cost effectively and move the industry, which we believed had potential to be among the most energy efficient, up to current levels of construction and beyond. Interestingly enough, the impetus for this work came from the industry itself. They saw the opportunity. They wanted us to lead this effort, and they've been strongly behind it through the Systems Building Research Alliance, the Manufactured Housing Institute, and other arms of the industry. We're going to talk about a suite of technologies that we have been working on in a combined way. These technologies will not be new, I suspect, to most of the people on this call. In fact, my guess is that many of the people who are listening in right now have used some of the things we'll be talking about. And our interest was in to take these technologies, adapt them for use in the factory building environment, and try to do so, as I said, in a way that was cost effective, as low cost, as affordable as feasible. So in approaching this problem, our efforts were, we looked to achieve three outcomes. The first was to demonstrate that these technologies in the factory setting were feasible, and that there were ways to incorporate them in the factory setting that worked in conjunction with factory building practices. Second, we wanted to treat all the contributors to space conditioning, HVAC equipment, envelope components, ventilation, air tightness, all the things that contribute to heating and cooling loads and indoor air quality, as parts of an overall system, and that together need to achieve both energy and comfort goals, but to do so at the least possible cost, and as I mentioned, the most cost-effective way. We refer to this overall goal of trying to balance different measures, but towards a very ambitious end as integrated design. It's a term that's probably now been overused, but it's handy. It's a handy catch-all for us to know that what we're trying to do is to balance a number of different building components that together provide a very energy efficient construction. And third, we wanted to develop a detailed understanding of how integrated design systems, when in practice, can enable us to fine-tune this overall approach and provide a meaningful guidance to designers. In other words, we wanted to do the research that was needed to be able to give the designers of factory-built buildings to begin with some guidance on how they should design their buildings, how to effectively use these technologies. So what we're going to do now is I'm going to provide a bit more of an overview of the project, a little past work that led up to the project, and then I'm going to turn it to my colleague Jordan Dentz, who will take you through the details of the system design, the testing that we've done, the evaluation, the results, and what we've gleaned from all of this work. And as I mentioned at the end, we'll take questions about the presentation, so we'll take some time for that. Okay, a couple of the basics here. While we're looking to come up with a system that produce very energy efficient construction for factory building, we also had the consideration that we wanted to reduce energy use by at least 50%. This is a Building America goal, but it's something that we tacked on here as an important starting point for whatever we came up with. That's not the limit of what we wanted to achieve, but that's the baseline, the basis that we wanted to at least achieve. And Jordan will tell you more about how we're doing thus far. The components that we looked at as part of our optimized or integrated design included an ultra-efficient thermal envelope, low-capacity, highly efficient mechanical systems, innovative distribution system, and affordable and effective ventilation. So we looked at these four components in combination to determine what combination of these components would get us 50% or better and in the most cost-effective means possible. We undertook a process that involved, well, I guess you could boil it down to 4 steps here. I'm sure there's a number of different ways to look at it, but we thought about it as in 4 different phases. The first was to design and then build and commission a prototype home that we could use to study this combination of measures. We would instrument that home so we could collect data about performance over both heating and cooling seasons, that we'd assess the performance of that home. And you'll see when Jordan goes through his presentation how detailed this analysis was and what we were able to glean from this study. Then we took the data and we dissected it, we diagnosed it, we critiqued it, and then we strategized on what it was telling us in terms of what was working and what wasn't working, so that we could glean from this process ways to do it better. Obviously, this is then the 4th step is refine the design. It's kind of a do the work, analyze the work, come up with conclusions, refine the design, repeat. So we're now into the 2nd stage of repeat, which Jordan will tell you more about. But we've gone through the first iteration of this entire process, and that's the basis of our presentation today. The core technologies are basically 3. You'll see a couple other ones related, but in essence, what we wanted to do is look at the main components. And for us, in terms of factory building, we needed to figure out ways to improve the construction and performance of the walls, developing what we called quote-unquote advanced walls. We looked at the roof construction. Again, I want to bring you back to the fact that what we're talking about here is manufactured or factory-built housing. So that's a little bit of a different environment and landscape for energy-efficient measures. So when we talk about advanced walls and advanced roof construction, we're talking relative to what the industry was doing 5 or 7 years ago. So the advances are against those kinds of technologies. And finally, we look to change out the equipment, which historically in manufactured homes has been a sore spot for energy performance. Typically, manufactured homes are built with furnaces, either electric or gas furnaces, and then site installed with some kind of either a heat pump or an air conditioner. There are all kinds of opportunities along the way for performance degradation. So we're looking for a solution that allowed us to alleviate those problems, the things that happen during transport, not so much during transport, but during setup of the site, and do as much in the factory where it can be under the watchful eye of the quality control people as possible. So we turned to ductless mini-split heat pumps as a solution that could be factory installed. It will give us the efficiency we were looking for, and were relatively inexpensive compared to some of the other options. So first, let me just chat quickly about the technologies. When we're talking about advanced walls, and as I said earlier, I suspect a lot of you are doing these things already. Our focus was on adding foam board to the outside of the home. Here you see a photograph of an early application of styrofoam to the outside of one of the manufactured homes that we built. We built about 15 homes altogether. Some of them just received certain products. Some of them had received the whole suite of technologies, and you'll see some of those examples. But advanced walls consisted of a frame construction with high-density bats and foam on the outside. In the case of ceilings, for those of you who are familiar with factory-built construction know, and you can see from this photograph, that one of the real challenges we have is that the amount of space available for insulation in the ceiling is rather limited by shipping heights for the homes, so the homes can only be of a certain height. So here you see the depth of the insulation at the eave is limited to somewhere usually between 5 and 7 inches, and it gets to the peak where it might be 17 or 18 inches, but still that's a far cry from what you are used to with site-built homes. So the question is, how do you improve the performance without changing the physical characteristics of the building? So one of the things that we worked on developing is, and of course to keep it within the cost constraints that we had in mind, one of the things that we worked on was using blown insulation, which you see here, blown fiberglass, but installing it in a way that increased the density of the product. Because typically the product is simply blown across the ceiling and it settles at its own density. We wanted to figure out a way to increase the density, so we came up with this idea. I'm going to show you, if you don't, I can do this, a video. What we came up with is, here you see the blower that's typically used in the attic for blowing insulation. We created this pegboard for dense packing the ceiling insulation. Very simple technique. We wanted to make sure we didn't slow down production too much. This slows down things a little bit, but not where production is king in the plant. We wanted to keep it from slowing down. So in each bay, the workers come along, they put the pegboard down, they blow the insulation under the pegboard, air comes up through the holes in the pegboard, and it packs it down dense, more densely than obviously you could do it otherwise. Therefore, that's increasing the R value of the insulation. And then they move it to the next bay, and they do the same thing, and they go down and do the entire ceiling in that way. And as you can see, you get to the left there, you see the dense packed ceiling insulation. Of course, it's dense packed and it's right up against the top chord of the truss. We had to use some kind of baffle to hold back the insulation because we wanted to make sure to ventilate the attic properly. So you can see here the installation of the baffles was an important part of this solution. Just a couple of comments about the installation of windows and doors. The foam presented some interesting issues in the plan for us. Putting it on the outside did change some of the thresholds to the doors, for the doors and the casing for the windows. But also windows are installed on the outside in manufactured homes, so they bear to some degree on the insulation itself, so we had to work that out from an engineering standpoint. Generally was not a problem, but there were some, as anybody on the call who's been involved with energy efficient construction knows, it's in that God lives in the details of these homes, and these details were critical to us to make sure that the home is tight and sealed up against leaks. And what they do in the plant, probably as well as anywhere, any form of construction, is to seal up the edges of the windows and the doors, and of course any penetration in the ceiling, in the envelope. One must say that if you've ever been to a manufactured housing facility, or if you haven't been to one, you'd be very impressed by the quality of construction. You'd be very impressed by the quality of construction and the detailing, particularly when it comes to the things like making sure there are no leaks and sealing up all the penetrations. There's just a great deal of attention that's given to the quality of construction in the plant. A few words about the ductless mini-split and why it's so attractive to us for factory building in particular, but I think this goes for any type of construction. No ducts whatsoever. That is for us a godsend because the ducts in a manufactured home are installed partly in the plant and partly in the field.
they're subject to or they're exposed to the opportunities for poor workmanship and leakage. Eliminating those entirely is in and of itself a major performance opportunity improvement. And of course, it eliminates that part of the site work that is associated with a home setup. Instead of ducts, we use transfer fans, and you'll see those as Jordan talks through his part of the presentation. Also, as I mentioned earlier, what we do like about the mini split, but we like it because it has an outside unit, one outside unit, and in our configuration, one inside head, a single inside head, is that it's pretty cost competitive. It's a little more expensive than equipment that's typically used, although it's less expensive than a site installed heat pump. But it's in the manufactured housing world and in the affordable housing world, it's a very attractive solution if you can, particularly if you can get away with only using one internal head. That's sometimes a tricky proposition, and we'll talk about that in a few moments. We do like the fact that these products come in very high efficiencies. As you know, the SEERs can get up in the 20s and 30s in some cases. HSPFs are equally high. We did have some issues with that, which we'll talk about. But in theory, the efficiency of the equipment is very high. I mentioned the factory installed piece of this. The fact that the entire product can be installed, charged in the plant was a big advantage from our standpoint, where it can be controlled by quality control. Control is much more easy. And also, since there is no furnace inside the house, it saves space, which if you're building a small home is really an important factor. Some other features of the home, and I'll mention that while this is all an integrated design in the way we described it, we also sought to meet all the conditions to certify this home under the Zero Energy Ready program, which is the Department of Energy program for high-performance buildings. So a lot of what we used here, the Energy Star appliances, not so much the windows, which were required for the envelope efficiency, but the fresh air ventilation, the air tightness, some of that related back to the Zero Energy home requirements. This was, in fact, the first, to our knowledge, the first Zero Energy Ready manufactured homes built in the country. Okay, just to give you a bit of a sense of what led up to this in terms of the research that brought us to where we are today. And this is now going back a couple of years. This is give you a sense of the flow of decision making and of experimentation that went on that brought us to the current work. A number of years ago, we wanted to look at foam on the outside of the walls as it would perform in manufactured homes. We did some racking tests with a company in California, and we developed some wall samples, put some foam on them, different sidings, and then we put them under stress to see how and if and when they would fail. So we wanted to get a sense of the structural implications of using foam. That led us to doing a prototype with foam walls with another home manufacturer in California. Mainly and partly what we were looking at here was initially how long it took to put the foam on the walls, because our goal was total energy cost reduction. And that's not just material costs. When it comes to factory building, the labor costs and the throughput of the plant are important and more important in some regards than the materials themselves in terms of costs. So we wanted to make sure that whatever we did not slow the line production down significantly, and that we integrated the product into the line and into the production process. So we worked with a number of plants to figure out best practices for installing these products. You saw the video of the dense packing. We actually experimented with different materials, different products. We looked at also packing in fiberglass bat insulation instead of the spray. So we constructed a home in which we had 7 different roofs, and we built them in different ways. We instrumented this little house to look at moisture flows, because we were also concerned about how the insulation and the thickness of the insulation and the placement of the insulation would impact moisture in the attic. So this was part of that experiment also in California. Finally, we looked at cool roofs as another alternative to see what kind of impact we could make here. And here's another little house we built with dense pack ceiling insulation, but five different roof finishes, reflective ceiling, and 5 different coatings of different reflectivities to see how these roofs would perform from a thermal standpoint. So we looked at thermal and moisture in this little house construction. So by the time we had finished all our little experiments, what we did is we worked with, again, another company out in California. California seems to be a very good place to do these things. Who built a whole house using both the advanced walls and the advanced roofs in California. And then we of course watched that from a production standpoint and evaluated the performance of this house. So that led us up to our current work. And by the time we had gotten to the place we are today, a series of questions presented themselves. And these became the research questions for the current work. The first question we had was about the Zero Energy Ready home, whether the program itself, the way the Zero Energy Ready program is designed, is suitable for manufactured homes. And if not, what changes would be required in the program to make it fit with the industry. Specifically, we wanted to know about mini split heat pumps. And this is really a fundamental question that I want you to remember as Jordan's talking about our experimentation. We wanted to know whether the mini splits with this essentially new distribution system, which Jordan will talk about, called transfer fans, can achieve the comfort targets that we desired for these homes. So we not only wanted great performance, we wanted to make sure that these homes are going to be comfortable and that they can be controlled properly. That was a large part about what our research was focused on. Of course, we were very concerned about costs because we recognized that if the overall cost of what we were doing was out of the range of what was practical or achievable or for the industry, it would never go anywhere. So we were very fixated on costs and figuring out ways to reduce both use of materials, figure out which materials give us the best thermal bang for the buck, and how do you apply those in a way that speeds up construction. And finally, and again, this relates to the mini split, how does it perform in service? And that's going to be part of what Jordan touches on. There were a series of other questions that arose as we started through the research. We'll talk about those towards the end. But these things framed our investigation. In addition to which, you know, the uber goal here was to see how do you take all these energy features and combine them in some synergistic way. So I'm now going to turn it over to Jordan, who is going to take you through our experimentation. You want to put this back in?
Okay, thanks, Emmanuel. So Emmanuel's giving you the background, what led us up to this work that we'll be presenting here. And I'm going to talk in detail now about some experiments that we did in Russellville, Alabama with 3 lab homes, as well as a 4th lab home that was built more recently in New Jersey. So we took the integrated design concept and brought it to life in one home that you see in the picture here and compared it side-by-side comparison with 2 additional homes. So there are 3 homes as part of this experiment. Home A is a standard HUD code baseline home. Home B is a manufactured home Energy Star program home. So it's an upgrade from the HUD code. And home C, the one closest to us in the photo, is the integrated design home. And this is a schematic of the integrated design home. All the floor plans were identical for all 3 homes. The only differences were in the energy specifications related to insulation, mechanical systems, appliances, ventilation. You'll see in this picture a series of arrows that represent the transfer fans, as Manuel has alluded to. The red rectangle outside of the kitchen, opposite the refrigerator, is the indoor unit for the fan, for the air handler of the heat pump. And the pink arrows represent fans that are moving air into the bedrooms and the master bathroom. And the green arrows represent return air flows back into the living space. The 3 homes were built outside of the factory in Russellville. You'll see them here in the top portion of the picture. The integrated design home is the one on the right. And these are the specifications for the 3 houses. Won't go into every detail here, but generally you'll see that House C has superior insulation to the other 2. Our 28 floors, our 18 walls, which is a batt plus the 5-inch of foam, better windows, ceilings with the dense packed fiberglass, and mechanical ventilation, which is compliant with ASHRAE 62.2, as opposed to the typical HUD code ventilation system, which is a fresh air duct to the return side of the air handler. I'll talk in detail a bit more about how that performed later on. Furthermore, there are no ducts in the House C, as Emmanuel mentioned, has the transfer fans, whereas the other 2 homes have ducts. On the equipment side, in House C, we have the mini split heat pump. In House B, there is a air source heat pump, as well as an electric furnace. And in House A, it is a typical straight air conditioner with an electric furnace for heating. A little more detail on House C. This is the flows that we were achieving with the transfer fans in our initial setup. And you can see that we have in the neighborhood of 50 to 100 CFM air moving into the bedrooms, which is not a lot. And later on, we increased that and achieved some better results, as you'll see later on. Each fan in this experiment was controlled on its own thermostat. So there was a small thermostat in each bedroom that activated the fan when the temperature got either too high or too low, depending on the season. And the ventilation, you'll see in the upper left where it says 45 CFM continuous, there was an exhaust fan providing the fresh air ventilation. So the commissioning results, again, House C has tighter air leakage, less air leakage. It has no duct leakage, of course. And houses A and B have an intermittent, look at the ventilation row, because of the method of ventilation there, they have an intermittent ventilation rate of between 32 for one house and 44 for the other house. And because it's intermittent, you're not getting ventilation continuously, and we'll see later on how that, on average, we're getting ventilation rates that are much lower. So those 3 houses were monitored for 1.5 years with quite an extensive data collection system, including temperatures in all the rooms and all the equipment power measurements, stratification temperature measurements, high and low in the rooms, and an exterior and outdoor weather station as well. So here's some of the data points: air temperature, humidity, condensation, measurements of moisture in the walls, rather, power consumption, etc. So these are some snapshot of some results over a 2-week or week-and-a-half period in late summer looking at the energy consumption of the three houses side by side, the houses A and B, the HUD code and the Energy Star house, consumed a similar amount of energy in cooling, 15 or so kilowatt hours per day. House C, the zero energy ready home house, consumed about half of that, and achieved a similar indoor set point average, about 76 degrees Fahrenheit. Humidity measurements show that the house C was a little bit more humid, although it's still within acceptable range. And the ventilation rates, as I mentioned earlier, in houses A and B, they were in the low teens on average basis. So they weren't getting the full ventilation rate. And that is probably one reason why the humidity in house C was higher, because it was bringing in more outdoor air with the full ventilation rate. This is the data on a scatter plot showing that cooling power relative to outdoor temperature. House C is much lower. Houses B and A were the green triangles are house C, the blue is house A, and the yellow squares are house B. Ambient temperatures on the bottom axis and HVAC kilowatt hours and cooling energy on the top axis, on the y-axis. So as temperature got warmer, the savings get more dramatic. And we also looked at comfort, because it's one thing to save energy, but we wanted to make sure that our cooling system was delivering cooling to all corners of the house. So the next few charts show the temperatures in each room over that same period. The bold red line in the middle is the set point, 76 degrees, and then we have a 3-degree band in either direction, which is the maximum variation per the ACA manual RS guidelines. Those are the dashed red lines. So you see house A had variation, but generally within the range of plus or minus 3 degrees at the set point in all the rooms. House B also had a tighter band of temperatures. Thermal envelope is more efficient. The solar gain on the windows is lower in that house, so it was more evenly more even temperatures there. House C, wider temperature range as expected, but mostly still within our 6-degree band there, with the exception of the master bathroom, which was 2 rooms distant from the source of cooling. So that room got a little bit too warm on the daily peaks. So we're in the ballpark here, but it's not perfect. Want to move on to some results for heating. This was in, again, a week-long period in November 2014. The average outdoor temperature during this period was 41 degrees. Kind of cool for Alabama, but we got lucky. Again, similar comparison, the heating kilowatt hours per day for house A, 49 kilowatts. House B was about 18, and house C 16.6. So much lower because of the heat pumps in those 2 houses. Average indoor temperatures, again, around 70 degrees, a little bit higher in house A. And humidities were all about the same. Again, you can see the ventilation effectiveness. Because of the intermittent nature of the ventilation in house A and B, they were only about a 10 CFM continuous on average basis. And we have our same comfort plots for these periods. House A in heating, pretty much using up the full range there, but staying within it. Here we have a 2-degree, again, 2-degree temperature variation, because that's the guidelines for heating. So 71 degree set point plus or minus 2 degrees Fahrenheit. House B, we dropped a little bit in some rooms because of the variability in distribution systems. There was Probably the design of the distribution systems was not completely balanced with the heat loss in the rooms. So as a result, we have a little bit of underheating in the bedrooms, but not too bad. House C, of course, with our transfer fans, had significant underheating down to the 60s in a couple of rooms, particularly that master bathroom and the master bedroom, which are the more difficult in this particular floor plan to communicate with the living room. So we found that we needed to add some resistance heat in those bedrooms, and we did that, and that maintained our temperatures. Of course, it added to an additional energy consumption factor, which we have to account for, and which you'll see shortly. But this is another cold period where we tested with the resistance heat and maintained the temperatures in those bedrooms. This is a similar plot showing the load lines for the heating energy. This is with the resistance heat. Again, House A is still much higher. House B and C are similar now because of the added resistance heat. And just some kind of a side note to look at the backup resistance heating in House B, which had a strip heat as a backup to the heat pump. You can see that below, once you get down below 30 degrees, below freezing, the backup electric resistance dominates the electric heating usage in the traditional heat pump. So here's the breakdown for House C during that same heating period, showing the blue, which is the heat pump energy, the red is the backup resistance heaters, and the little green is the transfer fan energy. So that's the total space conditioning energy for the house. There is a lot of resistance heat energy. It's roughly half of the energy, but it's providing far less than half of the heat. But it's necessary to get the heat into those bedrooms. So in conclusion, on the energy side for this house, we have found in this experiment, House B, which is the Energy Star house, used slightly less energy than House A for cooling. However, in cooling, House C used about half the energy of the other houses. In heating, House B and C consumed roughly the same amount once we put the resistance heat into the bedrooms of House C. And compared with B and C, House A used about 3 times the heating energy of those two houses. Again, this is a slide that shows the effective ventilation rates. On average, over the monitoring period, these are the ventilation rates that we measured based on runtime of the air handlers in houses A and B, and then the exhaust fan in House C. Interestingly enough, the HUD code requires for this size house 50 CFM. However, the ASHRAE 62.2 only requires 45, which is what this house was designed to. We did measure moisture in the wall cavities because we were concerned that adding foam to the walls would potentially lead to moisture issue inside the wall cavities. We did notice that the humidity in the walls in House C was a little bit higher. However, the temperature was higher in those walls by about 5 degrees minimum temperature. So the foam was helping keep the wall warmer, and we didn't experience any risky periods. We did not introduce latent gains into this house, into the homes. We did have sensible gains to simulate occupancy, but we did not have humidification in these houses. We also looked at monthly peak demand, which is something of interest to the utility, and found that House C, the zero energy ready home, had a far lower monthly demand. That's the green on this chart. House B, the Energy Star home, and House A House B was slightly lower than House A, but House C was much lower. The average demand reduction compared to House A was 69% for House C and 18% for House B. So going from a standard electric home to Energy Star saved about an 18% in demand, and going to the integrated design saved more than 2/3 in terms of peak demand. We also looked at attic temperatures to see that the dense pack roofing was restricting ventilation and perhaps causing unreasonably high temperatures there. We did see slightly elevated temperatures in the House C and some of those peaks, but relatively minor, a couple degrees C. So this was an interesting component of the work. We want to quantify the coefficient of performance for heating of the heat pump, and we measured it in two ways. We used a co-heat method, which you see in the photos on the right, in concert with tracer gas measurements and electric resistance heating, and then with an airside airflow measurement. So looking at the inputs and outputs of the heat pump in terms of temperature and moisture, relative humidity, as well as measuring, doing a flow map of the heat pump, so we knew we could predict what the performance was at any given time during the monitoring period. So we measured the COP in these two methods, and we did that for all the houses. We found that the COP for the electric furnace was a little more than 1, so kind of about what we expect, one for electric resistance heating. For the House B heat pump, about 2.5, and then for the mini split heat pump, we also came up with about 2.5, which was a bit surprising. We were expecting something more in the order of 4 or even higher for that heat pump. Those were using the co-heat method. We also used the air side method for the 2 heat pumps and came out with lower numbers there, 1.4 approximately. We trust the co-heat method measurements better, more, and so we're going with those for reasons which I'll explain here. We felt that the airside measurements had far more room for error in terms of uniformity of the air measurements and room temperature differences, as well as variations in convective airflow when the air handling units were operating. So we're taking the co-heat method measurements to be more closer to the actual performance. So we're scratching our heads and wondering why we weren't getting such good COPs with our mini split. One thing that we tested out was the fan speed, and we noticed that the fan speed, when it was on the auto setting, which is how we had left it, was always running on low speed. So we kicked it onto high speed, and lo and behold, we got a significantly higher COP with the high fan speed, 4.11 in these measurements here, as compared to 2.49 with the low fan speed. So that granted, we had slightly higher ambient temperatures during that measurement period, but that's still a significant increase in COP when we had more air moving over the coils at a faster rate, and we had more circulation in the room that perhaps reduced the recirculation or the short circuiting at the unit. So that was a lesson we learned, and look for ways to apply that lesson in future projects. Again, here's a comparison of COP as a function of ambient temperature with the fan on both high and low speeds. Again, you can see on the high fan speed, both air side measurements and COP and COE measurement methods, the COPs are significantly higher with the high fan speed. We also, as I alluded to, considered that short-circuiting at the heat pump could reduce COP. In other words, because these heat pumps are positioned high on the wall, and generally the equipment has been historically designed and intended for cooling, warm air coming out of the heat pump could rapidly rise to the ceiling and be sucked back in through the return without fully mixing in the room. We did find that air entering the heat pump during this measurement period at about 75 degrees, whereas the living space was in the 70-degree range. So that was, again, during low fan speed measurements, but a concern that could reduce performance with these heat pumps if not accounted for. So one of the objectives that we then wanted to do is to look at extrapolating energy use over a year in a variety of climates. And we did that with field-calibrated energy models using BUP with Energy Plus Engine. So we spent a lot of time calibrating the BUP models for all three houses to match the measured data over the measurement periods. We modeled 5 houses this way. So 3 of them were the actual houses as built, HUD code house with electric resistance heating, the Energy Star house with the heat pump, and the integrated design or zero energy ready house with the mini split heat pump. But we also threw in a few other variations, one being a HUD code house with a heat pump, and a second one which is the Energy Star house with electric resistance. So that's, you'll see this model A1 and A2, and then B1 and B2, those are 2 variations, a variation on A and a variation on B. So this is the whole house energy, site energy results using the Knoxville site for those 5 houses. Again, A1 is the HUD code house that was house A. A2 is that same house with a heat pump. B1, which had the Energy Star house with the electric resistance heating, and B2 is the Energy Star house with the heat pump, and C1, of course, is the mini split heat pump integrated design house. So there's a consistent drop in usage. Primarily, the heating energy is what's affected, although there is a difference in cooling as well. So more telling on the next slide, this is just isolates the space conditioning site energy, the same 5 houses. House C, total space conditioning energy compared to House A is about 45%. So we're reaching our target over the worst house. There are still a variety of ways of improving it, which we'll talk about in a bit. Just looking at the paybacks and the costs, Emmanuel mentioned and emphasized that cost is critical. We have here a couple charts. The first one is the houses compared to House A annual utility costs. So annual utility costs for House A, B, and C is in the left column of the top chart. And then the second column is annual savings. And then the third column is the incremental retail cost. So how much more would a retail buyer expect to pay once this home is in full production? For example, House C would cost roughly $5,800 more at the retail level and save about $600 a year at utility costs for a payback of about 9.7 years. This is our first cut at the first house with some projections, but we think these numbers are in the right direction, something that the industry could adopt with some further refinements. So I'm going to turn it back over to Emmanuel for a little bit. He's going to talk about the research questions again and how we've addressed them with this work.
Okay, thanks, Jordan. So just to recall, there were 4 research questions that we started with. The first one was, can you build a zero-energy home in a manufactured housing environment, and what changes would be required? I think when you read through these 4 points, you come to the conclusion, yes, you can do it. We didn't seem to have that much difficulty in meeting the requirements. There were a couple of specific items that we had to talk to DOE about, but ultimately we were able to build this without jumping through too many hoops. Just to highlight a couple things that Jordan mentioned, the thermal envelope and the ventilation, the indoor air quality requirements, while not a barrier, they added to the costs. The cost of $5,000 to get up to this house is a bit on the high side for the industry, but it's, as Jordan mentioned, it's doable, and our expectation is that as a first cut, we're very likely to do much better than this going forward. And so, in general, zero energy ready does not provide a barrier for the industry, and the industry ought to be looking at this pretty seriously. Mini splits, I think Jordan's laid out the case. They perform pretty well in cooling. Again, I want to kind of back up and remind you that these houses were in Alabama, so this is a cooling-dominated climate. And in that location, they did pretty well in the cooling mode, primarily with the doors open. And with the doors closed, things start to change a bit because the airflow becomes a little bit more iffy, but still, well, not too bad on the cooling side. Heating was a bit different matter. As Jordan showed you, those charts indicated that House C struggled at times to maintain temperatures in the remote spaces, the bedrooms, that were near or within the 2-degree band that ACCA requires. Doors open, not so much a problem, but doors closed, then you start to get some issues. A couple other findings. Open doors may obviate the need for transfer fans. I think that's kind of part and parcel of what I'm trying to say here about the performance results. And this stands to reason. When you close a door, you're basically you're now down to your fans in terms of the air movement, and you're prisoner of your fans. When the doors are open, there's much more mixing that's going to be going on between the spaces, much more likely that there's not going to be horizontal stratification of temperature. So if you can keep your doors open all the time, you're home free. Closed doors, which is the reality in the world, is more consequential during the heating season, at least in Alabama. I'm going to talk in a second about our experiments in heating climates. Window shading, we closed the blinds. We looked at some variations of changing the amount of sunlight coming through the windows. That does prove to be, as you would expect, intuitively, has a real benefit in terms of cooling energy savings. Again, it's a customer implemented measure, so it's undependable, but it does make a difference in terms of energy use and comfort. There was a fair amount of convective heat transfer through the open doors, as Jordan mentioned. Comes back to my first point. And this is the important finding here. The transfer fans are of limited values when the doors are open, but they're of real value when the door is closed. How much and what size fans is still a research question for us. And the transfer fans in the low-high configuration, which is how we had it. Air came in low on one side of the wall and exited high on the other side, was not particularly beneficial. Second question had to do with costs. You saw the more detailed cost that Jordan showed earlier. House C had a 50% space conditioning savings compared to House A. That's pretty much the target we were shooting for. Probably even got a little bit better than that. Strategies are available for reducing backup heat and increasing mini-split COPs. which should substantially improve the results. So the paybacks should get even better as we make refinements to the design. And the equipment improvements have a larger relative impact of energy use than the envelope. In other words, we can add more insulation as you might expect. It's of diminishing returns. Our focus at the moment is on doing a much better job with the equipment. That's where we think the biggest bang for the buck is going forward. That being said, it's already a pretty great thermal envelope. And how do the mini splits perform in service? You heard about the COPs. Both the conventional and the ductless were about 2.5 before we started investigating why. That is well below the expectation that we got from the manufacturer's data, and this is probably true for any mini split. And when we changed the setting to high speed, of course this is one of the core findings, we got in the neighborhood of what the manufacturer was estimating. So that these small things do matter, and how you set things up are important in terms of achieving performance goals. Moisture, I think we found that the moisture issues, we were concerned about there might be some moisture buildup in the walls over time. We did not find that to be the case. There were some slightly elevated moisture or humidity levels in home C, but well within safe limits. By and large, RH, and this is at Alabama, it gets pretty hot and wet there. We're within acceptable limits, although the latent loads were not simulated, which means we didn't dump a lot more moisture into the space to simulate cooking and people in the space and washing. So that is something that remains to be done. Peak loads, as was discussed, averaged about 18% lower for House B relative to A. A whopping 69% lower peak with C versus A. That's a big hit for a load. Very attractive outcome. Some House B winter peaks were similar to House A. This is not totally surprising, indicating B's peak occurred about the same time as A. And if you want to read about all of this in the full report, here is the link. And I think that is being made available to you by NREL. Just click on the link and you'll be able to download the full report. And we're going to love to hear your feedback on it. I will, before I turn this back to Jordan for some more comments about what we're doing next, I wanted to mention that there are two short summaries of the work that are also on the NREL site, the DOE site that NREL can point you to. One has to do with the house itself, and one has to do with the attic insulation technique that you saw earlier in the presentation.
So this is Jordan again. Just going to bring it around to what we learned from that and how we're applying it to another test house. How much time do we have left? About 10 minutes or so. So we're taking the work that we did in Russellville and we did some further experiments. This is the refine step in the design, and Manuel mentioned early on in the presentation in our 4 steps of our process. And looking at some improvements or opportunities for changes as we also move to a cold climate and build a subsequent test house as a 2nd generation integrated design manufactured home. So I'm going to talk for a few minutes here about some modifications we looked into and experimented with related to the ventilation system, the distribution, and the thermal enclosure. So we really would like to have heat recovery ventilation instead of just an exhaust fan. We looked at 6 options using BOPT, Building Energy Optimization software, in a variety of northern climates where we would expect that to be more attractive in terms of a total energy related costs per year metric. And this plot shows those 6 items. There's 3 different HRVs. 2 exhaust fans, and then just a balanced ventilation without heat recovery. The Broan HRV, you can see is aside from putting aside the non-recovery balanced ventilation, the Broan has the highest cost, followed by a Panasonic Whisper Comfort 100 CFM unit, and then the lowest source energy consumption unit was the Panasonic Whisper Comfort 40 CFM unit, which unfortunately doesn't have quite enough flow for providing the full required ventilation. As a result, and the other two, you see a Broan and an Air King exhaust fans. So you'll see all these are pretty much in the same ballpark, though, in terms of total energy-related costs. They're not, none of them are, aside from the balanced ventilation, are that dramatically different that it would drive the cost in and of itself. But because we're dealing with an industry that has certain processes and procedures and is used to using exhaust fans, there's not a good reason. We haven't found a good reason yet to change to heat recovery, at least of the products that are available yet. We would like to get heat recovery ventilation, but we're still leaning towards using the cheapest, low first cost, high efficiency exhaust fan. So no change there. On the distribution side, however, we did want more airflow. We wanted quieter fans. We didn't think we needed the high-low configuration, so we tested out retrofitting some. These are Panasonic bath fans that are going straight through the wall. They're lower power and higher flow, getting up to about 150 CFM. So we retrofitted them. This is the same. This is house C again. You can see the 4 boxes in that panoramic photo in the plan on the bottom, showing where those fans were retrofitted. And okay, there we go. The monitoring results with the new fans showed that they're basically equivalent as to an open door. These plots show the indoor temperature on the left for each of 3 rooms, 4 rooms actually. I'm sorry, for each of 4 conditions. The left plot is a small bedroom, bedroom 3, and the right plot is the master bedroom. The set point is about 74 in these plots, and you can see that everything is except for the red triangles, everything's pretty much clustered together, and those conditions are shown in the key below. The blue is with the doors open and the fans on. The black is with the doors open and the fans off, so you can see when the doors are open, the fans really don't matter. And then the yellow is with the doors closed and the fans on. So when the doors are closed, the fans provide effectively the same, nearly the same indoor environment as opening the door does. When you turn the fan off and close the door, however, in the red triangles, you can see the temperature drops off dramatically. So we're also moving to, as we go to a colder climate, more efficient windows, wall insulation, more floor insulation, and a tighter envelope. This is a plan of the new house just completed, built by a factory in Pennsylvania and set in Eatontown, New Jersey. A very similar floor plan. Those blue arrows indicate where the fans are, and the blue rectangle is the heat pump location. Some photos of the new house. Again, it's similar foam on the walls, similar dense pack in the eaves, on the roof. This house had sprinklers, so we had to deal with that challenge, air sealing the ceiling. You can see a photo of a box going over the sprinkler head on the left in the ceiling. And on the bottom right, one of the transfer fans being installed in the living room. This is the house being installed on the site. We'll be monitoring this house for 6 months in an unoccupied state starting around now, and then 1 year while it's occupied, we'll be monitoring it. So this will be the first occupied, monitored house of this type, integrated design, manufactured home. Also Zero Energy Ready Home certified. Got a ribbon cutting last week. Some dignitaries, you can see a picture of the finished house. Some of our monitoring equipment. This house will have solar panels as well. It'll be net zero when those are installed. We do have some initial data from some cold snaps that we had earlier in April. And looking at the bedroom temperatures over the span of about a week. The blue line towards the bottom is the outdoor air temperature. This is all in Celsius. I apologize for the change in units, but it ranges from about freezing to about 10 or 15 degrees C. When the transfer fans were turned on, you can see that the temperatures start collapsing. The bedroom temperatures come up close to the heating set point of 23 C or 74 degrees Fahrenheit in this case. When the temperature falls down to the 5 to 10 degree range C, there's a bit of a spread in those bedroom temperatures on the right of the graph, a little more than we would like, exceeding our, I don't have the bands here, but that does slightly exceed the 2 degree Fahrenheit band, so we would need a little bit of resistance heat to bring those back into alignment. So that's just some initial data. We'll be continuing to monitor this house for the next year and a half, and we're excited to see how the our family that moves into it feels about it. So next steps, again, we're going to continue working on this new house in Eatontown. We will be implementing full internal gains, both sensible and latent, so moisture as well. It was mentioned early in the presentation that we're also working with Habitat for Humanity, and we're taking some of these same principles and applying that to 2 homes that we're going to be building with Habitat in New England. And those homes are being designed right now. Furthermore, we'll be building 2 more manufactured Zero Energy Ready homes in New York State as a part of a project with NYSERDA using many of these same principles. That'll be a 3rd generation of those homes. So that takes us through the presentation, and we're ready to take questions.
All right, great. Thank you both very much. We have some questions from the audience, and you can also submit additional questions through the pane on your screen. We'll answer as many as time allows. The first question is, were there low VOC materials requirements for IAQ?
Yes, we followed the Zero Energy Ready home requirements for Indoor Air Plus. And we didn't actually have to change anything about the materials that went into the home that the factory had normally used.
Okay, great. Did you measure humidity levels within the set of homes given the geographical area?
Yes, we did measure humidity, both at the weather station and in the homes themselves, as well as in the attic and the crawl space. So all that data is described in the full report. Okay,
great. Was there any thought to using an IR camera to see cold spots on the ceiling at critical area?
We did a little bit of that. It was inconclusive. We didn't identify any significant issues that jumped out at us. I was more interested in looking at the floor because of the way the floor system is built with the frame and the joists, in some cases, in some locations, compressing floor insulation significantly. Was curious to see if we would see any bridging, thermal bridging in those locations. But again, we either didn't have the right conditions or we weren't able to identify anything when we looked. But when we moved to the house in Eatontown, presumably we'll have some colder periods next winter. We'll be able to look at that more again.
Okay, great, thank you. Did you measure the home's air exchanges with a door blower test?
Yeah, we did a multi-point blower door testing. I think I showed the commissioning results early on. If I remember correctly, the blower door test results in house C were about 3.8 ACH50. In houses A and B, they were a little less than 5. That is a continuing challenge. You would like to be able to get those numbers down, and as you might imagine, in a fast-paced factory building environment, we build it. The homes are tighter than I guess tighter than traditional site-built construction was a few years ago. However, getting below the 4 or 5 ACH50 requires some is challenging. We're developing techniques for that, not least of which is the marriage line when you bring the two halves of the home together, which is done on site. That is even with a marriage line gasket, it is still a source of leakage that needs to be addressed.
Okay, great. What was the impact of using a mini split heat pump on the HUD temperature rating of the home versus the standard home design?
Can you repeat that?
What was the impact of using a mini split heat pump on the HUD temperature rating of the home versus a standard home design?
Yeah, I don't think there was. I'm not sure I fully follow that. I don't think we had an impact on if the questioner is asking about the heat load calculations. The mini split was designed to meet the required load per the calculations that the manufacturer did. But maybe I can answer more detail by email if there's more detail to the question.
But the mini split was designed to take the heating load.
Yeah.
But the HUD code requires that all the homes, all the spaces in the home, all the living spaces have a direct heating source, which the resistance heat provided. We obviously want to minimize the amount of resistance heat, but the equipment itself has to take the equipment itself was sized for the load of the entire house.
Okay, great. How do the homes perform in shear strength during the transportation with XPS sheathing? Are there any issues with drywall cracking?
We did not experience that, and that was the purpose of some of the testing that Emmanuel described earlier that was done in California. The house C that was in Russellville, I believe the foam sheathing replaced a foam core board, so there wasn't, except for I think some shear walls at the corners, there was not wood sheathing on that house to begin with. But yeah, we did not see any cracking, and those tests that we did bore out that it was acceptable.
Yeah, the foam doesn't add much in terms of structural rigidity or bracing effectiveness. And I believe all the homes we looked at had OSB underneath the foam.
I don't see. Not many of the AB or neither of those did. Just the
some of the ones we built in California had OSB because of the earthquake and other requirements out there. But what we did, so the foam doesn't do much for you structurally. What we did notice is occasionally, depending on the material you use for the siding, it could add some to the rigidity of the home, particularly if you use a cement board. Vinyl doesn't do much for you, but if you put a cement board, even though it's outboard of the rigid, it still provides some racking strength. But we, as Jordan said, we didn't see drywall cracking on these homes.
The homes in Russellville were vinyl wallboard.
Okay, great. Has ARIES had the opportunity to study the impact of large-scale heat pump systems used with modular assembly for affordable housing in the United States? The Boulder County Housing Authority is currently replicating the lessons learned for a large-scale heat pump systems at a project in Colorado.
No, we haven't had that opportunity yet, but we'd love to.
Okay, great. Someone was asking, they said it was somewhat surprising that House C did not have a much lower heating energy use. Do you have any theories about why that might be?
Well, the primary theory is that the mini-split COP was not what was expected. It was about the same as the traditional heat pump. And then that plus the addition of the resistance heat brought the heating energy for House C up to about the same as House C. Yeah, also we had about 3 times the ventilation in House C, which puts an additional load on the heating system.
Better air exchange, but more electrical energy use.
Yeah.
And as Jordan is indicating, if the COP gets back up to what we expect it to be, making with proper adjustments, we would then expect to see the heating side savings.
Okay, great. I think that's about all for questions right now. Emmanuel and Jordan, before we have the audience take a quick survey, do you have any closing remarks you'd like to make?
Well, we certainly appreciate everybody joining us today and the good questions. We're very anxious for the results to be shared with other people, to get more questions and critique and ideas put on the table. I hope you'll feel free to contact us and with any ideas and just to share your own thoughts or to talk about how we might collaborate on things. So we appreciate NREL's sponsoring this event and look forward to doing more of these.
Great. Thank you both so much for your time and expertise. I did want to address a question about where the report can be found. I'm going to put a link on the Building America meetings page on buildingamerica.gov, so it will be found there along with the link to this webinar presentation. At this point, we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us know what we're doing well and where we can improve. The first question asks whether the webinar content was useful and informative. Please take a moment to choose your answer. The second question asks about the effectiveness of the presenters. And the third question asks whether the webinar met your expectations. Right, thank you for answering our survey. You can subscribe to receive notices about upcoming webinars and other news at the URL on the screen. On behalf of the Building America program, I'd like to thank our expert speakers for their time today and to our attendees for participating in today's webinar. We've had a terrific audience and we very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.